So, all right, good morning.
Morning.
Morning, yes. So last time we have reviewed, the theory by Bohr and Sommerfeld about the atom models. So, but there is a fundamental difficulty of the stability of atoms. That's related to the light-matter interaction, because if the atoms can radiate, and then suppose the energy will just going to zero, so the atom will not be stable, right? So this is what we have learned. So then the essential thing is about how to reconcile the theory about the atom and the theory of light, which were by that time, going mostly independently. By then, there were a lot of interactions between the two, and Einstein, Bohr, Landberg, Kramers, Seidel-Born, and a number of pioneers actually made the key contributions to understanding the interaction between the atom and the light, and that eventually will lead to the revolution of quantum mechanics. Okay, so this is the key actually problem in the old quantum theory. Right. Using Bohr's quantum theory, concepts of photons, statistical mechanics, thermodynamics, so that's already known by the time of 1916. So Einstein actually can derive Planck's law of radiation. Okay, so I don't want to go to details into this one, but he introduced basically two coefficients. One is the absorption, induced by the light. Another is the spontaneous emission, of light by atoms. And then he found that by thermal radiation, thermal equilibrium, there's also emission induced by the light. And these two actually will be equal essentially to the absorption induced by light. So these are called AB coefficients, which of course later become important in the lasering theory. But at that time, that was important to introduce these transitions between atoms, and the levels in atoms by the emission and absorption of light. So that was an important concept. Okay, let's skip this formula. But anyway, Einstein can kind of derive this Planck law just by using these concepts. Okay, and this actually is the early manifestation of what later was embodied in Bohr's correspondence principle. And this, of course, is also a key touchstone for Heisenberg to invent his matrix quantum mechanics. Okay. And then Bohr proposed the correspondence principle. That was a very useful tool in the old quantum theory to derive or to calculate the optical properties, the spectral properties of atoms. Okay, so the basic idea is that if we consider an orbital of atom, and this atom should have this also like orbiting frequency, right? So the frequency, of course, is given by the velocity divided by the circumference of the orbit. Okay, that's nu c. This is very easy, and this one, of course, is by just a little bit of calculation is proportional to 1/n cubic. N is a quantum number. Okay. And then he said that, of course, according to classical electrodynamics, you know that the radiation of the light must be multiples of this frequency, right? If you have orbital, a periodic orbital, and then the radiation must be a multiple of this one. This is classical mechanics. But in quantum mechanics, it should be the transition. So this frequency should also be the difference between the two states, two levels in the atoms. How can you make these two to be equal? And Bohr found that if you have this quantum number to be large, and then you find that the change of the energy, because of the change of the quantum number, it's exactly the same as this multiple of orbital frequency. So that was a remarkable observation. And then he proposed that this actually a correspondence between the classical mechanics and quantum mechanics, not quantum, quantum theory. saying that if you have the quantum number to be large enough, and then the two results must be more or less the same. Okay. And basically, you say that so if you change the quantum number from n to n minus tau, that's a transition, right? And then according to quantum theory, the frequency will be the change of the energy due to this change of quantum numbers. But if n is large, you can replace this change by the differential. Okay, that's a tau times the change of the differential of energy with respect to the action. So that's nothing but just the classical orbital frequency. So this is a very interesting result. So, but the important thing is that so he was taking this orbital as a periodical thing. So the transition frequency is just given by multiples of this this orbiting frequency. Okay. And so that means you can take this as almost like an oscillator, right? So the oscillator has this frequency, 2 pi times the integer and times the frequency of this orbital, and times t, right? So the emission will be given by, of course, just the dipole. That's the charge times this oscillator displacement. Okay. So then, he said that we must therefore expect that for larger values of m, these coefficients will be on the quantum theory determine the probability of a simultaneous transition from a given stationary state, for which m equal to m prime to another state. That's n equal to m prime prime. That's m prime minus tau, right? So that's what we have for show. Okay, and this of course had a lot of applications in the early days for calculating those selection rules, polarization of emissions, understanding Stark and Zeeman effect, and so on and so forth. Okay, okay. It was important in the older quantum theory, but the most important thing is was used by Landenberger. Okay, and that was to calculate to understand the dispersion theory. So what is dispersion? That means you pass the light through a medium, and then this light actually will be separated into different colors. So that's called dispersion. That's because the response of the media to this light of different frequencies or different wavelengths will be different. Okay, in mathematics we say that there's a response. The linear susceptibility depends on the frequency omega, and that will be you will have this kind of difference dependence if you have an oscillator with a frequency omega I. Okay, so this is the dispersion of an oscillator to a frequency to a light of frequency with frequency omega. And then you compare this one to the Einstein theory, you can find out a more quantum susceptibility theory. Okay, but this is a formula, not the point. The point is that so if you look at the atom transitions, so the emission of light by atoms can kind of understood as that for each transition there is a virtual oscillator. So as if the atoms contains many oscillators, each one has a frequency that's equal to the transition frequency. Okay, so this was the idea by Landenberger. Okay, but of course this one was not perfectly correct because it has only emission. You should also have absorption, right? So that means you needed to have two terms. Okay, you have a transition, you have absorption, you should also have emission. Okay, so the absorption is a minus sign. So that was improved by Kramers and Heisenberger. Okay, so you can see that Heisenberg already entered into this kind of calculation using these virtual oscillators. Okay, and then Slater actually make a further extension by saying that that's not only this oscillator associated with the atoms, but there's also virtual fields in the vacuum that interact with these virtual oscillators that cause this absorption and emission. Okay, but then there's obvious difficulty in this kind of light atom interaction because the transition in the atoms are discrete. And then this electromagnetic wave treating as a classical oscillating wave, has a continuous momentum and energy. So how can you have this energy and momentum to continuous in the electromagnetic wave, but discrete in atoms. So that was a difficulty. And then Bohr, Saito, and Karamis, they actually proposed a very radical idea, saying that the energy and momentum may not be perfectly conserved at this atomic scale. It could be just statistical. Okay, you average up to energy conservation, momentum conservation, but at the atomic scale, they are not conserved. This was proved wrong by the experiments, carried out by Compton and Salmon, and also Bose and Geiger. They were using a device invented by Curie to count the number of electrons and X-rays, so that they can measure the energy conservation and momentum conservation individually. Okay, so that was important. But still, the key point from this old quantum theory is that the atoms have these virtual oscillators. Okay, so the radiation, all those things actually are related to these oscillators. Okay, and that's related to the transition between the two states. Okay, and also they introduced this idea of so-called fluctuation, statistical conservation, and this will later become important in understanding quantum mechanics. Okay. So let's just to do a quiz quickly, talking about this correspondence principle. So this actually is the only key idea in this part. Okay. So we have 5 options. So the correspondence principle means A, each transition in an atom corresponds to a virtual oscillator, and B, each virtual oscillator corresponds to a virtual field. And C, each quantum process will approach to a corresponding classical one when the quantum number is large. And D, each symmetry corresponds to a conserved quantity. E, none of above. Can we just take a look at these options? Okay, let me show the result. So the correct answer is the answer that most people chose. It is C. Okay, so the correspondence principle means that you can actually have the quantum process approach to the classical one if the quantum number is large, or if the quantum object is like a microscopic object. And A actually is an important consequence of this correspondence principle. Okay. So if you to have this one, and the Landenberg come up with the idea that we should have an oscillator that is associated with this transition. Okay. Right, but then and the old quantum theory was actually quite successful in understanding the spectral properties of atoms. Okay, even to calculate the selection rules, polarizations, and the dispersion relations, so on and so forth. Okay, but however, it's logically incoherent because it's partially classical, partially quantization, and then to have the calculation to be correct, and then you have to make some limit using this correspondence principle to got some numbers by comparing the quantum results to the classical results. Okay, so there is definitely something unknown in the quantum theory. And you have to still use the classical physics as a kind of a crutch, as a touchstone. Okay. So Jammer actually commented that the old quantum theory is a lamentable hodgepodge of hypotheses, principles, theorems, and computational recipes, rather than a logical, consistent theory. Okay, that's a fair comment. Okay, and also, of course, it's difficult to apply this one to helium and other multi-electron atoms. Okay, and more fundamentally, more importantly, so the stability of atoms was not yet understood. Okay, it was still kind of ad hoc, requirement of this old quantum theory. Just assume that there were levels, and those levels are just stable. The others are not, so which were not understood. So then it was a kind of dilemma. Okay, people at that time didn't know how to proceed. Actually, they know that there must be something fundamentally different and something interesting there. But what is it? Okay, so that was the question. And then they come to the real light, okay, by Heisenberg. Okay, so this is what we have learned, right? And then Heisenberg, actually based on the a method, a theory proposed early by Born. Okay, Heisenberg made the key breakthrough. Okay, let's see what it is, and then that one will lead to eventually a systematical theory of quantum mechanics in the matrix format. And Max Born actually tried to extend the Kramers-Bohr-Slater Riemann theory on the light-atom interaction. And he was trying to extend this theory to the interaction within multiple electrons. And in that case, you need not only to choose to treat the force because of the electromagnetic wave, but you also need to treat the force between electrons. And so what he tried to do is that what we shall do is to bring the classical laws for the perturbation of a mechanical system caused by the internal couplings or the external fields into one and the same form. So that means even if you don't have electromagnetic waves, you consider only electrons. So you have no way to escape this quantum theory, right? Because you cannot treat the other electron as classical and this electron as quantum. So that means you need to treat all the quantities in a kind of consistent way. Okay, so this was the insight by Born. Okay, so then he said that we should not only choose this, do this correspondence for the frequency of the light and the frequency of the orbit, but actually you should do this one for all the physical quantities. Okay, you should have the correspondence principle. And you find that if you look at the frequency of the light, it's given by this energy difference. Okay, that's given by this energy divided by the action. Okay, and he said that actually the differential of this energy with respect to the quantum number can be written as the energy difference divided by the quantum number difference. And then he said that then you can generate this into any quantum, any physical quantities. So for phi, and then the change of phi, the differential of phi with respect to the quantum number, actually should be replaced with the change of this quantity as a function of this quantum number to another one. So this actually is very important. So basically you change a quantity to a quantity to two quantities. So you only look at the difference between the two. Okay, so this is an important insight. And then comes Heisenberg. Okay. The Heisenberg actually was a very young student. He was born in 1901, so that means in 1925 he was only 24 years old. Okay, so he studied on the Sommerfeld in Munich on the turbulence. Okay, so he had a very good training in classical mechanics, and actually Born already supervised him in this study. And then when Bohr gave a talk in Göttingen on his quantum theory in 1922. He actually attended the festival. okay, and got familiar with the old quantum theory. And then after his PhD, he assisted Bohm in Göttingen and also Kramers in Copenhagen with the calculation of dispersion, stack effects, and multi-electron atoms. Okay, so he was familiar with those, correspondence principle in those calculations. And then during his stay in Copenhagen, actually he interacted with Bohr, and he understood that Bohr was deeply concerned with the fundamental concepts of the old quantum theory, and his concern was, about this concepts relation to the experimental observations. So not like so Bohr was a nice kind of concern with those calculations. So Heisenberg then was motivated to think about deep into these questions. Okay. And then in his first paper, the important paper about this matrix quantum mechanics, he wrote that the present paper seeks to establish a basis for theoretical quantum mechanics founded exclusively upon relations between quantities, which in principle are observable. Okay. So we are trying to only consider these quantities observable, not about those things, even true in classical, real in classical mechanics, but not observable in the experiments. So he said this correspondence principle, the Einstein-Bohr frequency condition, always represents such a complete departure from the classical mechanics, or rather from the kinematical, from the kinematics underlying these mechanics. That even for the simplest quantum theoretical problems, the validity of classical mechanics cannot be maintained. So that means it seems sensible to discard all hope of observing hitherto unobservable quantities such as the position and the period of electron. So he was trying to abandon completely the concept of orbits, so that the position of the electron is not observable, and so the period of electron actually is not a good concept. It seems more reasonable to try to establish the theoretical quantum mechanics analogous to the classical mechanics, but in which only relations between observable quantities occur. So he was trying to wonder, so in the experiments, what kind of things were actually observed? It was the frequency of the light, okay? It was transitions. It was not the orbital. It was not the position of the electron, okay? So he said that we should just write down this theory in terms of this kind of transitions, in terms of this kind of oscillators, these frequencies, between the two states, not actually in terms of the frequency of an orbit, okay? So the key idea is that the position of the orbiter is not observable, but instead only the component, the oscillator, the virtual oscillator, X, that's defined by two quantum numbers, n and n minus tau, the initial state and the final state. So that is associated with the transition frequency, omega n and n minus tau. Only those things are observable, okay? So then the new theory must be the theory about these observables, about these quantities between the two quantum numbers. Not there is no such kind of thing called an orbital that has a frequency given by m, okay? There's the only things that has a frequency given by n and n minus tau. So that was a deep, it's a kind of a jump, okay? So that means in Bohr, you say that there's energy quantized, and Bohr said that anything should be quantized, but you still have an orbital. So anything is a function of an orbital m, okay? And Heisenberg said no, we don't have an orbital. So you don't have a function of orbital. You only have transitions between different states. You have two quantum numbers. So then you should have everything just written in terms of n and n minus tau, not just rather as a function of m, okay? So that is something important, okay? So that means you should write down the displacement x, in the older theory is kind of like a functions of m, right? But now you should write this x, as kind of components between n and n minus tau. Each of this one has a frequency omega n and n minus tau. So everything is kind of between n and n minus 12. Okay. So there's no such kind of things that you have an observable that is a function of m, but instead you should have something that's observable. You know, it's a function of n and n minus 12. But then he's trying to combine. So if you combine, for example, 2x, so you have x squared, for example. And then if you calculate the intensity, of course, you need to calculate x squared. And the x squared is also a quantity. And then you should also have this combination. But then, you know, if you just put it directly, then, you know, by a naive way, you find that there's a difficulty. The difficulty is that if you still define everything as n and n minus 12, and then the frequency is n minus 12, n minus 12 top prime, or n minus 12 plus eta. And then you do the combination, you find that the frequency is not correct because in general, you know, this two frequency, you know, the transition from n to n minus eta and the transition from n minus 12 plus eta is not the same as omega m from n to n minus 12. But instead you have, of course, the race combination principle. This is easy to understand. You have a transition from n to n minus 12. That would be the same as you first do the transition from n to n minus eta, and then to n minus eta to n minus 12. Right. So this is very easy to understand nowadays. Okay. But then at Heisenberg's time, of course, you needed to do some massage of this expansion of the position into the oscillators to make the correct frequency combination. And then Heisenberg come up with the correct translation from this classical orbital to the quantum oscillators. So he said that in the combination, you have to do the combination like this one. You go from n to n minus eta, and then to n minus eta to n minus 12. And then this will, of course, naturally you're going to have the frequency and to satisfy the correct combination rule. Okay. And then you can do the same thing for the combination of x and p, the momentum, right? So you can have the transition for the x from n to n minus eta, and then for the momentum for n minus eta to n minus 12. You can combine the two. You also have the right oscillating frequency. But then there's an immediate surprise. That is, if we exchange xp and px, because they're occurring between different transitions. So that means xp and px will not be the same. Okay. So this was a surprise at that time, okay? And he applied this one to a few simple examples, okay? Which actually lead to the correct results known by the old quantum theory. And then Heisenberg, you know, come up with this revolutionary idea, but he was not very confident. He sent the manuscript to Born to let Born to decide whether or not to publish it, and went on vacation. He was kind of conservative, okay? He said that the positive part of the paper was poor, okay? However, Born, after reading this manuscript, understood it, immediately appreciated the importance of the paper and sent it for publication, okay? And Born wrote that after having sent Heisenberg's paper to Z Physica for publication, I began to ponder about his symbolic multiplication. That's the combination rule of, for example, x and x, x and p, p and x, so on and so forth, okay? I was soon so involved in it that I thought the whole day and could hardly sleep at night. For there was something fundamental behind it. And one morning, I suddenly saw the light. So what was the light? He found that, look at this one, the transition, the oscillator associated with the combination of x and p between n and n minus 12. In Heisenberg's combination is for x, n is a transition from n to n minus eta, and then for p is n minus eta to n minus 12. So combine it together, you got a transition from n to n minus 12. But this one is nothing but just like a matrix product. Okay. So Born realized this is a matrix product. And then he calculated the diagonal matrix of elements of this matrix product. He found that if we look at the x and p and px, they do not commute. That means they cannot be exchangeable. They are not exchangeable. Okay, xp do not equal to px. But they found that this is actually equals to I times Planck constant over 2 pi. This was a surprise, a big surprise. And this one is fundamental because it related to the only number that's important in auto quantum theory. That's the Planck constant. The Bohr realized that the significance of this formula, the long commutativity of the product xp and px, was directly related to quantum processes at the atomic level through the appearance of Planck constant. And so and then of course this is a conjecture because he only calculated the diagonal matrix elements. So he asked Pauli to work on it to try to prove this one in general. But Pauli was reluctant. He said that, yes, I know you are fond of the tedious and complicated formulations. You will spoil Heisenberg's physical ideas by your futile mathematics. So Pauli declined the invitation. So Bohr turned to Jordan, okay, and Pascal Jordan. And Jordan developed the matrix mechanics and proved the famous commutator xp minus px equals to IH over 2 pi or IH bar. And then Bohr and Heisenberg Jordan wrote a systematic paper in 1926, presented the full theory of matrix quantum mechanics. Okay, and they also quantized the angular momentum, and they consider both discrete and continuous states, spectral. Sorry, they don't have states. But they still didn't solve the problem of a hydrogen atom. Okay, so they couldn't compare this one to the Bohr's successful theory of atom model, you know. Okay, so the hydrogen atom problem and the Balmer spectrum was still left unsolved. Okay, so the three-man paper, however much it struck right at the heart of the quantum mechanics, did not yet produce the answer, much to their frustration. And Pauli actually during that time was kind of sarcastic about this matrix quantum mechanics. And Pauli felt that the 43-year-old Bohr should leave the problems of quantum physics to the new generation of young physicists. And one must first seek to liberate Heisenberg's mechanics from Göttinger's deluge of formal learning and better expose its physical essence when he was writing to Kronig. And Pauli actually was writing alone. And Heisenberg was frustrated. And he challenged Pauli by writing him that, with respect to both of your last letters, I must preach your sermon and beg your pardon for proceeding in Bavarian. It really is a pigsty that you cannot stop indulging in a slanging match. Your eternal reviling of Copenhagen and Göttingen is a shrieking scandal. When you reproach us that we are such big donkeys that we have never produced anything new in physics, it may well be true, but then you are also an equally big jackass because you have not accomplished it either. So this actually is a very polite challenge to Pauli. Pauli was a smart guy, okay? He couldn't stand this kind of challenge. He wanted to beat them just in their own games by solving the hydrogen atom problem using the matrix algebra. But it was not easy, it was difficult, okay? But anyway, Pauli responded by beating the three men in their own game. He derived the Balmer formula using the new matrix mechanics with the trick of using the lens operator, which is technical, okay? We should not be concerned here. In only 3 weeks. So that was remarkable, and that immediately attracted the attentions of the whole community to this matrix quantum mechanics. Okay? And Bohr wrote to Pauli saying that Kremers, Kronig, and I, who have just gone once again with the greatest pressure through your beautiful calculation of the hydrogen spectrum, send you many friendly greetings from Password. Okay, so that was the excitement of Bohr. And in the meantime, okay, a young student in Cambridge, Paul Dirac, after reading the paper, the first paper by Heisenberg, who gave the manuscript to Paul Dirac's supervisor Fowler in July, okay, of 1925. And then he worked out beautifully the algebra of this quantum mechanics. He independently invented this matrix quantum mechanics and give all the fundamental equations. Okay. And established the correspondence between the classical and the quantum mechanics. That was beautiful. So he reformulated this matrix quantum mechanics. He found that in the classical mechanics, there is so-called a Poisson bracket, which is given by the differential with respect to the momentum and the coordinate. Okay. And then, of course, in classical mechanics, the time dependence, the time derivative of physical quantity is given by the Poisson bracket between the Hamiltonian and this quantity. Okay. And in classical mechanics, the Poisson bracket of momentum and position is 1. And between the position and the momentum is just -1. And then he found that correspondingly, you can define the commutators between two quantities in quantum mechanics. So AB minus BA, which is just given by the Planck constant divided by 2 pi I times the Poisson bracket. Especially for XP and X and P, the momentum and the coordinates is XP minus PX. That will be I times H bar. And the time derivative or the evolution of an operator of physical quantity A will be given by the Poisson bracket between the Hamiltonian and this physical quantity. So this is remarkable. So you can actually almost formulate the quantum mechanics in the exact same form as the classical mechanics. Okay, so you have a beautiful correspondence between the classical mechanics and the quantum mechanics. Except that in the classical mechanics, the physical quantities are commutable. Okay, but in quantum mechanics, so they are not commutable. So the commutators actually is given by H over 2 pi I times the Poisson bracket. Okay, so that he catch the key difference between the quantum mechanics and this classical mechanics in the algebra. Okay, and he introduced, of course, the Q numbers and C numbers, and also he independently solved the hydrogen atom problem. So that was a systematic, beautiful work. Okay. Okay, and he wrote to Heisenberg, and Heisenberg wrote back. Saying that I have read your extraordinary beautiful paper on quantum mechanics with greatest interest. And there can be no doubt that all your results are correct as far as one believes at all in the newly proposed theory. Your paper is also really better written and more concentrated than our attempts here. Remember, this was before the 1926 paper by Heisenberg, Bohren and Jordan. Okay, this was in November. So you can see the how far Dirac has gone. Okay, and Dirac, of course, submitted his PhD thesis with the title "Quantum Mechanics" in May 1926. So this is a kind of a summary by taking the quiz. Let's do the poll. So why did Heisenberg introduce matrices to characterize a physical quantity? So A, because if the Hamiltonian is viewed as a diagonal matrix with diagonal elements, the other physical quantities should also be matrices. B, because he thought only the components associated with the transition between two states is unobservable. C, because he knew matrices have discrete eigenvalues, so could account for the quantized energies. And D, because he knew X and P do not commute in quantum mechanics, but the real numbers or complex numbers do. So they must be matrices. And E, none of above. Okay, so let's stop right here and show the results. Most people chose D, and but the correct answer actually should be B. So Heisman actually at that time was not familiar with the matrix mathematics. Born, of course, in Göttingen, he was well trained in mathematics, and he had some good friends, and knowing very well about those matrix mathematics. Okay, but Heisman was driven by this physical understanding of the radiation by atoms. He's saying that all the radiations actually are related to the kind of virtual oscillators. That's defined by the transition between two states, not defined as a function of one state. But in the Bohr's theory, all the quantum theory, each electron has so that has a frequency. And Heisman said, no, there's no such a thing of orbital that has a frequency. The frequency is only defined between two states, not associated with one state. So he abandoned those kind of frequency as a function of a state, but he used the frequency as a function of two states. So that means the oscillator should be between two states, and so the position should have two components, two indices associated with the two states in the transition. Okay, so that one comes giving this idea of this expansion of the position into components with the frequency associated with the the transition of two states. Right, so this is what has been achieved by 1926, mostly by Heisenberg, Bohr, and Jordan, Pauli, Dirac, okay, about this quantum mechanics in the matrix algebra, okay. It was remarkable, but it was difficult to proceed. And then there was another line of the theory of the story. So coming from this photon as particles of waves. And then there's also, some kind of quantum stuff in understanding those transitions in atoms. So that means the light, the quantum of light is also related to the transition atoms. Okay. So that comes the great idea by De Broglie about this wave particle duality. Okay. He introduced a kind of wave for the electrons, just like a wave for photons. So he said that photons can be, the light can be a wave and a particle. So how about the electron? Should electron also be a wave and a particle? And this one was, of course, a revolutionary idea. And that one eventually leads to the, the wave quantum mechanics by Schrödinger. Okay, so we can take a break at this point and then continue the story. Okay. So the new breakthrough, on another line is made by De Broglie in introduction of the matter wave, and this one, of course, was based on the wave-particle duality, understanding of photons of light, mostly done by Einstein. So in the Einstein's 1996 paper, we talked about earlier on emission and absorption. He actually also studied the momentum of a photon. And so what he was studying is that he considering the molecules embedded in a gas of photons. And then these molecules, there are very few molecules. So the molecules were just like particles in Brownian motion embedded in the liquid or the gas. So they will be bounced back and forth by those photons. He was trying to study the thermal equilibrium between those molecules and the photons, okay? Right, and then he calculated the momentum fluctuation of molecules at the thermal equilibrium, and given the result to be 2R times K times T. And this one, of course, was exactly the same as those molecules if they bounced back and forth by themselves, each other. That was a remarkable result. That means the photons should also have individual momentum. So he said that so instead of frequency related to the energy, in addition to the frequency related to energy, and this reference should also relate to the momentum. Okay. So he said that all the going radiation is in the form of a spherical wave, does not exist. During the elementary process of radiate loss, the molecule suffers a recoil of magnitude h nu over c in a direction which is determined only by chance according to the present state of the theory. So what Einstein was saying is like this one. So if there's a molecule and there's a dipole that's oscillating, right? So there's a positive and negative charge. And if it's oscillating, so you know that there will be radiation like this one to both sides. Right. So this is a classical radiation theory. But in the quantum theory, so this is a molecule. So it emits the photons into one direction, and the molecule actually will be bounced back into another direction. Okay, so that the momentum is conserved. So in each individual event, the molecule and these photons actually go into a certain direction. Okay, so this is important insight. Okay, so it's not like a spherical wave produced by the oscillating of a dipole. So the light has not only frequency, the energy quantized, but also the momentum quantized, and take values. But now, unlike the energy is definite, the momentum will have random directions, right? Okay. And then this idea was verified by the experiment of Compton. So Compton did the scattering of X-rays, and this is a very nice device. He was passing the X-rays reflected by the graphite attack. Okay, and then he observed the wavelengths of this scattered X-ray light. And this was possible because of the invention by Van Lower and Brock, so that you can use a single crystal as a grating to analyze the frequency or the wavelengths of the X-ray light. Okay, so if you have different frequencies or different wavelengths, after diffraction by a single crystal, the X-ray will arrive at different position of this ionized chamber. So you can look at so you can measure the frequency. And then that's what they have observed. They say that at different angles, so of this scatter light, X-ray, you actually see the different intensities. Okay. So this one can be understood by the scattering of a particle by another particle. So the energy will be changed, and the momentum will also be changed. And according to Einstein's theory of momentum of the light, you find that you can actually have this change the reference lambda prime minus lambda is given by this angle. So you can see that the distribution of the scattered light in the reference actually depends on the scattering angle. Okay, so this one is in good agreement with Einstein's theory. So of course this was taken as an important experiment, verification of the idea of Einstein, taking photons, light as particles like photons. So that means it's well established now. The light, on the one hand, is a wave. On the other hand, is kind of a particle. So this is called a particle wave duality. That was fully established by Einstein theory and competence experiments. And and then how to understand the interference of light in the classical experiment. So Taylor actually in 1909 already did a very nice experiment. So that one can understand why the light can still have interference like a wave, but is also a particle, okay? According to Einstein's 1905 paper. So the experiment was done like this one. He used a filter to reduce the intensity of the light source, of the light from the source. So the light will eventually become very feeble. And they're going to pass this double slit and arrive at the photographic plate. And then you can do the experiment for a very long time. So this is because at that time you don't have this CCD camera, you don't have those CMOS camera. What you had is just this photographic plate. That means you did an experiment, and then you take the plate to the dark room, and you expose it, right? And take it to a dark room, and then you use the chemicals to show the picture. Of course, because the light is very, very feeble, that means most likely you just don't see anything. So you just put this plate at the position of this screen. If we do this one for a few days, okay, you process the this film, and you see nothing. Okay, you don't see, or you see just some randomly dots on this film. So that means the light actually arrive at this film randomly at different position. You can see that it's like dots. So it's like particles arrive at this one point by point. And then you do this one. If you leave this plate, behind this double slit for a few weeks, you can see that you can identify there's some kind of patterns emerging. Right. And you can wait for a few weeks. So the patterns become more pronounced. And if we do this one for a few months, actually, indeed, you see the very well presented, exhibited fringes, just like what you would expect to observe using the classical wave. So you can see that if you have the light at a very, very weak intensity, so they indeed behaves like photons, like particles. They just arrive at this one by one, similarly. And then you wait for a long time, they actually arrive like a wave, okay? So the wave behavior is a phenomenon that's accumulated by many, many shots of light, okay? So it's not if we do this one, we just say a single photon, one particle, you don't see a fringe, you only see a spot on the screen. You do two photons, you see two spots. You do with three photons, three spots. And you do 100, 1,000, and 1 million. And then you can see the fringes emerging as kind of build-up of histogram. Okay, so you can see this fringe can be taken as kind of histogram of a statistical process. So that was a really remarkable experiment. I think this experiment was not given sufficient attention by that time. Okay, I think it's even more important than competence experiment in understanding this wave particle duality of light. Okay, so we will come back to this one later. Okay, with more understanding. So now you can imagine that the experiment was done like this one. So this was actually Taylor's experiment. Okay. So if you just shed in the light, it's a particle. But this particle can pass through this double slit simultaneously. But arrive on the screen randomly at different positions. So if we just accumulate this one, okay, by one day you got one spot, or 2 days, 2 spots. You can actually, so you can say that every time you only have one photon, one particle passing through this device. So because you only recorded one, you can take away this film. You replace this with another one. You can put all of this one together, right? Okay, but if you accumulate more and more data, so you can see that they start to build up into a histogram. Okay, so the interference pattern, interference fringes actually can be understood as a histogram of a statistical process of individual particles. So now this is actually very puzzling because the photons or the particles, each time there's only one that passes through this one, right? But they can still interfere, okay? But eventually got this one, right? And of course, nowadays people have this CCD camera. So they don't need to wait for days, weeks, a month to accumulate this one using a very feeble light. They can do this much faster, okay? And this one can be done very nicely. And there's a demonstration, for example, in 2008, there are many such kind of experiments, okay? So this is a kind of a newly, performed demonstration. So you can do this one frame by frame and take the frame and you can take the frame home. Okay, actually you can have many of these devices at different positions. One in Hong Kong, one in New York, one in London, one in Shanghai, for example. Each one can take a frame. You can have different students. Each student take a frame. And then you put all the frames accumulate together. Actually, starting from some random spots on the screen, you have some kind of things emerging, very noisy fringes. But eventually, if you have many, many fringes, you have a very clearly exhibited interference fringes. Okay. That was a very nice demonstration of this kind of build up of the fringes, like a wave, out of those individual behavior of a particle. Okay. Okay, so this is the experimental facts about this kind of single photon interference. The first time, each time at the most, there's one click on your screen. So that means it's not interference between two photons because it never had two photons passing through your device. And at each time, the position of an individual click is random. You cannot predict where this photon will arrive at your film. The third point is that if you have many events, many shots accumulated, and then you're going to have the patterns to show up. And also, if you, each time, so I haven't talked about each time, if you just close one state, let this photon run up, pass through the one state. And by next time you close another state. So that means each time if the photon, the light only passes one state, actually there will be no interference pattern. Okay. So that means the photon has to pass these two states simultaneously. Otherwise, there will be no interference pattern, no matter how you set up which one is and when which are open. And actually, even if you have the two states open simultaneously, but just if you have some way to know which state the photon pass through, the interference pattern will disappear. Okay. For example, you can have a kind of a scattering light at the slit. So if one photon passing the slit, there is a recorded, scattering. So you know that the photon passes one slit instead of another one. So once this is known, actually, the interference pattern would disappear. So this remarkable phenomenon was summarized by Paul Dirac in one sentence. So each photon, the interference only with itself. Interference between different photons never occurs. So this is a very deep understanding of so-called quantum interference, or the interference of particles. So it's a wave-particle duality. So actually, the quantum inference is the interference between different possibilities of a single quantum object. So you can say that if there's only one possibility, or if you know the possibility, and then there will be no interference. Okay, so it's not between the two physical objects; it's the interference between different possibilities. So this is something that's important for understanding quantum mechanics. The quantum interference is not interference between physical things. It's interference between possibilities. It's interference between informatical things. Okay? It's about information. It's not about the physical entities. So the intensity of the light actually is kind of related to the probability. The amplitude is related to the probability amplitude. Okay, so we will come back to this one later. So this is for photon. Okay, for the understanding of photon. Okay, and then to further establish this idea of photon, so there's Bose actually just assume these photons are identical particles, so that you can have 1 or 2 or 3 and any number of particles with energy h times nu. And then you can calculate the average population that's given by the number of moles divided by this kind of e to beta. Beta is 1 over kVt times the energy minus 1. And then you can easily derive the energy density. That's the Planck formula. Okay, probably you have already learned a little about this one in the access class. So Einstein, of course, appreciated the significance of this paper, and he used this one to calculate the fluctuations of the energy and found that there are two terms, right? There's energy fluctuation due to the particle nature of this light, and also due to the wave nature of the particle. That's the one already known in thermodynamics. Even you assume that the light are waves. And he actually also extended this one to atoms and come up with this idea, this discovery of the Bose-Einstein condensation, which nowadays is also a very important field in physics studies. Okay. And he calculated the fluctuations of, of atoms. He found that also of these radiations, they found that there are two terms. One is of this particle, another of this kind of waves. He said that it arises in the case of radiation from interference fluctuations. May also interpret it for gases in a corresponding way by associating with the gas in a suitable manner, a ray phenomena, and then computing the interference fluctuation of the latter. So this is remarkable. This is already a hint that atoms can also be taken as a particle and a wave. Okay. So this is a huge insight. Okay, and then this insight was taken by De Broglie, and he wrote 3 important papers in 1923, presenting his theory of matter waves. Langevin reported his work in the 4th Solvay conference in 1924. Okay, and given the manuscript to Einstein. Okay. So you know that in Einstein's theory about the photon, so there's energy given by Planck constant times the frequency. There's also momentum that's given by h over the wavelength, or h bar times the wave factor. Okay. And then De Broglie just make a first direct analog, saying that the frequency of this wave of a particle should also given by the energy. So that is mc squared, of course. M is the rest mass times gamma. Gamma is 1 over square root of 1 over v squared over c squared. And similarly, this momentum should be related to the wave factor of this matter wave. Okay, so that is given by h over lambda. right? And then you can calculate this. So the matter wave can be written in this relativistic way. So that is I omega t minus I k times x. Okay, k is the wave factor, omega is the angular frequency, x is the coordinates, and t is the time. Okay, and then you can of course calculate the phase velocity, which is given by how fast the phase moves from one position to another position. It's given by omega divided by the wave factor. And this one, you can see that it's just given by gamma square. Okay. Times v. So then this one is equal to c square of v. And this, of course, is greater than the light velocity. It seems to be unphysical, but it's okay. Okay. Because what matters is the group velocity. That's the change of the wave packet. So if you use the different waves to form a wave packet, so there's a group velocity. So we are going to have more mathematics on this one next time. Okay. And the group velocity is given by the differential of the frequency. The angular frequency with respect to the wave factor. So that one turns out to be a very nice, nicely equal to the velocity of the particle, just in classical mechanics. So this all makes sense, right? So the velocity of a particle is the velocity that this wave packet can propagate. Okay, so that one carries the energy and the information. Okay, and the paper was sent to Einstein. Einstein said that this it's a very important paper, and actually De Broglie went even further. He said that there's a relation between this wave dynamics and the classical trajectories. Just by comparison between this matter wave and the light wave, we know that in the light wave theory, there is a Huygens principle, but there's also Fermat's. There's also another principle called Fermat's principle that tells how the light will propagate like a particle in a ray. This is called geometric optics, right? So the rays of the phase waves are identical with the paths which have the minimal phase. Okay, this corresponding to the least action principle for classical mechanics, and De Broglie discovered this relation between the wave dynamics and the trajectory dynamics. And he also discovered this standing wave, this quantization condition proposed by Bohr and Sommerfeld. He said that if you have a wave, make this wave around a circle, around a closed path. And you know that if a wave, the phase around this closed path must be integer particle multiple of 2 pi, right? So that means you have a standing wave. So then you can have a standing wave of 1 node, just like n equals to 1. Or you can have a standing wave of 2 nodes, that's n equals to 2, and so on and so forth. And then you calculate this phase along this standing wave. That is nothing but just the length divided by the wavelength, right? Okay, times 2 pi. So by the wavelength, one of wavelengths is nothing but just the momentum, right, up to factor of h. So that means the momentum integrated over this closed path must be an integer times the Planck constant. And this, of course, is a very natural derivation of the Bohr-Sommerfeld quantization condition. It's just saying that the waves within an atom has 2 form a standing wave. Okay, so that you can have 1 node, one node, 0 node, 1 node, 2 nodes. You have different number of nodes of this wave. So you have different orders of standing waves that give you the quantization condition. So that's a very beautiful and natural account for Bohr-Sommerfeld's quantization condition. Okay, and actually he also even proposed experiments to test his theory. He said that you can use a string of electrons. There could be waves like photons, right, passing through a sufficient narrow hole, and then you can exhibit the diffraction phenomenon. He was proposing that diffraction of electrons to see this kind of wave behavior of electrons. In his PhD thesis defense, he was asked by the committee, which was formed, which composed of Curie, Cartan, Lanzhuan, and Moguen, and about the possibility to test his theory in experiments. And De Broglie replied that maybe we can use diffraction of electrons by crystals. He already proposed this one. And his paper was sent to Einstein. Einstein read this one, was deeply impressed. He said, I should discuss the interpretation in greater detail because I believe that it involves more than merely an analog. And actually, he brought this paper to Boehm, and Boehm brought this one to Frank, who was the department head in Göttingen. And also Boehm talked to a student, Sasser, and Sasser proposed to Frank, said, we can do the experiment. And Frank replied, said, there's no need because Davison's experiment already showed these effects. Frank was mentioning Davison and Kussmaan's 1921 experiment of the electrons scattered by nickel surface, which showed some structures and angular distribution, just like diffraction patterns, which of course was not understood until Frank. And Frank's insight was that this was just diffraction patterns. But Davison was not actually fully convinced. So he continued his experiments by scattering electrons using nickel crystals. And he did this experiment beautifully by heating up the nickel crystal to high temperature and then cool this down and have the recrystallization so that you have a better crystal. I can say that after the recrystallization and this diffraction patterns, this angular distribution becomes sharper. So showing clear evidence of the diffraction patterns of electrons. So this was a very beautiful experiment done by Davison and Germer in published in 1927. So this was actually done years earlier, okay? But they didn't publish until 1927. And there was another experiment done by George Paget Thomson in 1928. And he passed the electrons through the gold films and showed this kind of rings. And this rings can be perfectly explained by the diffraction of waves passing through, crystal particles. Okay, and this was done by 1928, and of course, I got a Nobel Prize for this work, verifying the wave ratio of electrons. And this George Thomson was the son of another Thomson, J.J. Thomson, Joseph Thomson. And Thomson, the father, was awarded the Nobel Prize for having shown that the electrons is a particle. And Thomson, the son, for having shown that the electron is a wave. And both of them got Nobel Prize. Okay, so the family got 2 Nobel Prizes for finding out the 2 opposite natures of electrons. So this was in the book, was remarked by German in 1989. Of course, there's an important application of the wave nature of electrons. That is the transmission electron microscopy, because the electron has much shorter wavelengths than light, so it gives much better resolution in the imaging of materials. Okay. And there's a modern demonstration of the wave particle duality of electrons. So there are actually 2 experiments before this one, but Arika Tonomura in Hitachi did the most beautiful. Okay? So he used the high energy transmission electron microscope to perform these experiments. So the electrons are emitted by this electron gun one by one, passing through a double slit. Okay. And then observe the interference pattern. So the experiment done was like this one. So this is a movie. Can you see the movie?
Yes.
Okay. So actually, he can see this kind of spots showing up in the screen one by one, randomly. Okay. Because the electron was shot one by one by the electron gun. So indeed, the electrons are like particles. But then wait for a longer time, there will be more and more shots by the electron gun. So you can see more and more spots on the screen recorded by the camera. Right? You see more and more. It's just like still randomly, but then there are kind of thousands and thousands of shots of electrons. Okay. It's still something like a random, but if you have good eyes, you can see there's an emergence of noisy fringes. Okay. And then more and more. So you see the wave nature of this. So the wave nature actually is kind of probability distribution is a histogram of the random positions of the electrons. Right, so this not only show the wave particle nature of the electrons, but also the nature of these waves. It's kind of like a probability amplitude. So this is the summary of these beautiful experiments. So the result is the electron is a particle, but its probabilities propagate like waves. So the interference pattern is the pattern of this histogram. Okay, so this is a summary of quantum interference. And by looking at these experiments done by photons and done by electrons. Okay, so it's between different possibilities of a single quantum object. Right, so recently there are also even further demonstrations of this kind of wave particle duality by doing experiments with carbon-60 molecules, which has many electrons. Okay, 360 electrons, 360 neutrons, and 360 protons put together as a whole thing. So you can see there are waves. Okay, and there are also superposition and interference of many electrons form the superconducting phase in the SQUID, the superconducting quantum interference device. Okay, so there are 2 to the power 20 or more electrons. There are many others, like the mirrors in LIGO, like lasers, like Bose-Einstein condensations. So they all show this kind of wave or quantum wave natures. So now this is the quiz about we have learned about this early theory and experiments and the intriguing experiments about this quantum interference. So which of the following statements is or are incorrect? A, only the same kind of particles can interfere. Different kind of particles cannot interfere. B, different particles can interfere. For example, electrons can interfere with the photon. C, quantum interference must occur between more than one particles. D, quantum interference is not between different particles, but is between different possibilities of the same particle. The particle can be a photon, an electron, a molecule, or even a macroscopic, not a macroscopic, sorry, macroscopic object. E, none of the above. So let me show you the poll. So can you choose the one that's not correct? The incorrect one, not the correct one, okay. So which of those statements are not correct? okay? So the answer is that B and C are incorrect. So D, of course, is the most important facts statement about the quantum difference. So quantum difference is not between different particles. It's between different objects, possibilities of the same particle or the same object. So that means different particles actually they cannot interfere. Okay, and quantum interference, actually should occur between the particle itself, not between different particles. Okay? And this one is correct because first of all, you can only have the interference of between different possibilities of the same particle. So they must be of the same kind, right? But it's not fundamental. So most important one is this one. Okay, so this is correct. So in principle, you should also choose E, right? Because logically, it is none of the above is incorrect, but they are incorrect. So this one should also be chosen. But that's okay, just logical. Okay, so we learned the important thing about the quantum difference and the wave-particle duality. So what is the duality? So duality is that it's a particle, okay? But the wave is the possibilities of a particle is a wave. Right, so this one will lead to the important theory by Schrödinger. And then use the unification of the two theories, the matrix quantum mechanics and the wave quantum mechanics. Schrödinger was born in 1887. So by 1925, he was kind of old by that standard. Okay, by this day's standard, he's still very young. Okay, he was 38. Okay. But if we compare to Pauli and Heisenberg, he was the older generation, like Born. Okay. And Schrödinger starts his correspondence with Einstein to discuss the Bose-Einstein condensation, the statistics, in 1925, early 1925. And then he got a copy of De Brois's paper, which was cited in Einstein's second paper on the Bose-Einstein condensation. And he was asked to give in a colloquium at Zurich in December 1925 on De Brois's ideas. And during the colloquium, and Dubai and proposed that why don't you just come up with a wave equation, and you have a wave, but how would the wave evolve? What would change the wave? So you need a wave equation. Okay. So Schrödinger responded and said, okay, I will do it. And then he did it. And this is the equation. Now we are very familiar with. Right. So this is the Schrödinger equation. So we've spent a lot of time on this one, okay, in this course. So don't worry about this formula at this point. Okay. Okay. And in his paper, he said that above all, I wish to mention that I was led to these deliberations in the first place by the suggestive papers of De Broglie. And now, according to this Schrödinger's equation, the quantization arises naturally. And because if we solve this differential equation, partial differential equation, with the boundary conditions, you will get a so-called eigenvalues and eigenfunctions. So this become eigenvalue problems of a differential equation. And this method was rapidly welcomed, much better than the matrix form quantum mechanics by the physics community for various reasons. First of all, the differential form was very familiar to the physicists at that time, much more than the matrix. And also this wave function kind of has some kind of physical meaning like a matter wave, right? So it can be visualized. It's intuitive. And solve the differential equation is easy for a hydrogen atom. So you have a very easy solution and of this hydrogen atom problem, and harmonic oscillators, and many others. And also it's easy to apply this perturbation theory so that you can calculate those interactions between many electrons, so that you can look at the spectrums of those multi-electron atoms, like a helium, like other atoms. So then this theory become immediately popular. Okay. But there was a question. They simply there were two theories. They don't like each other. Heisenberg said that the more I ponder about the physical part of Schrödinger's theory, the more disgusting it seems to me, because Heisenberg was still talking about the position of the electron, right? But Heisenberg said that there's no position, okay? There's only transition. And Schrödinger's impression on matrix form quantum mechanics was not better. He said that I was discouraged, if not repelled, by what appeared to me a rather difficult method of transcendental algebra, define any visualizations. But Schrödinger was trying to find out why the two theories seemingly totally different and can produce the same results. So he actually found out by taking those differential operators, okay, and interpret as the momentum and the position. He found that the momentum can be actually interpreted as a differential operator in his differential equations. And this seems these are differential operators. Then you can easily calculate that, find out that x and p, they are two operators. They do not commute. So xp and px are different. Okay, so you can find out that xp minus px equals to I h bar. And this was the most important fundamental relation in the algebra of the matrix form mechanics, quantum mechanics, because Dirac has shown that using this one, you can actually derive everything else for the matrix form quantum mechanics. Okay, so that means Schrödinger can derive the matrix quantum mechanics using his differential equations. But now, this one is not fundamental. This one is actually a consequence of his differential equation formalism of quantum mechanics. There were also other efforts, in unification of this Schrödinger's waveform quantum mechanics and Heisenberg's matrix form quantum mechanics. Okay. So people later on realized actually they were equivalent. You can go from this to that or back and forth. Okay. And then there was interpretation. And Schrödinger's interpretation was kind of still following de Broglie's idea. He viewed this wave function, the modulus squared of wave function, as the weight function of the distribution of charge, so that this one times the charge density equals to this proportional or equal to this wave function modulus squared. Okay. And he actually used the coherent oscillation of a harmonic oscillator. We will come back to this one later again, okay, as an illustration. But of course, as we discussed earlier, okay, this one was not consistent with the experimental observation. And because in the experiment, for example, on the single photon interference or the single electron interference, we indeed see the electrons arrive on the screen point by point, not as a wave, not as a wave packet. Only the possibilities show up as a wave. So this interpretation could not be correct, as was pointed out by Heisenberg and Born. First of all, it cannot explain the double slit experiments done with photons and done with electrons. And it cannot explain the quantum measurement. Okay. And the PHYS in general is not defined in the 3D real space. For example, later on, we talk about spins. And spins is not a function in the real space. Okay. Even though this Schrödinger's interpretation of de Broglie's matter wave provide a useful intuitive picture for semi-classical understanding, they are fundamentally wrong. Okay, so we have to abandon this kind of interpretation. Instead, Bohr give an interpretation which is consistent with all the experiments done so far. Okay, he said that it was almost self-understood to regard the PHYS modulus squared as the probability density of particles. So that if you have two waves, for example, PHYS1 plus 2, the probability will be PHYS1 modulus squared plus PHYS2 modulus squared, and plus PHYS1 times PHYS2 complex conjugate plus PHYS2 times PHYS1 complex conjugate, give you the interference. So the quantum interference is this histogram of the possibilities. It's not a wave packet of particles. Okay, so you cannot take a particle as a small wave particle, a wave packet, but instead you still have a particle at the fundamental level, but they have different possibilities, and this possibility is probably like a wave. So per se, the wave function is a possibility wave. So I have to emphasize this one again and again. Okay, so this is the most important thing in understanding, if it can be understood at all, of quantum mechanics. Okay, so understanding of quantum mechanics. And the mystery of this quantum mechanics only deepens over time. Okay, so quantum measurement and the uncertainty principle, I would say, has never been fully understood, even by today. And there was Copenhagen's complementary principle, saying that you cannot once you got more information about this one, you can got more information about that one, got less information about that one. So they were complementary philosophically. So we never had a complete picture of this universe. You only got a complementary information about it. And Einstein challenged that the quantum mechanics was actually not complete, because you can have a quantity that has a well-defined value before your measurement, but it does not show up in your theory. Okay, so and he saw that he actually come up with the entanglement of particles as a sort of experiment to prove quantum mechanics is wrong. But then Bell come up with a simplified version, and they come up with inequality to test whether or not Einstein was correct. And so far, all the experiments, even though there could still be some loopholes, show that Einstein actually was wrong, and quantum mechanics is correct. And all about the measurement. And the measurement, quantum measurement, and Ugly say that there's a classical device and there's a quantum object. And during the measurement, the classical device will record a random results. Okay, and the quantum object will collapse into another state corresponding to the results of this classical device. But we know that there's only one universe. Where do you draw the line between the classical and the quantum? So this boundary is moving nowadays by the experimental technology. People now can prepare a quantum object of larger and larger size. So the line, the borderline between quantum and the classical is moving to larger and larger scale. So fundamentally, there's no reason to set a boundary between the classical world and the quantum world. So there's always a fundamental difficulty in this quantum measurement theory, even though we will still, for the operational reason, still use this measurement principle in quantum mechanics. But we should understand that there is a fundamental difficulty, because in the measurement theory, we have to say that there's something classical, there's something quantum. So the universe is not consistently described by one quantum theory when we come to this measurement problem. So this is the elephant in the room, okay? And there's many solutions. There are many solutions. One intriguing solution was provided by Everett in his famous paper on the universal wave function, popularly taken as the many-world theory. Okay, if you're interested, you can Google Everett's many-world theory. Right. So this actually complete the story we covered in this 1.5 week. And of course, there was another splash, important progress. That's actually the second half of the first quantum revolution. It's a unification. It's a combination, not a unification, combination of the special relativity and quantum mechanics. That leads to the Dirac's equation, the discovery of positron, the anti-electron, and the understanding of spin, and more importantly, the quantum field theory. Okay, so that will be the second half of the first quantum revolutionary, and actually was the most important thing until 1970s in the theoretical studies in physics, starting from 1925 to 1975 or 1980 probably. So there are a few things that we have not covered in this story. Left out. First of all, this relativistic quantum mechanics, the Dirac equations, and the discovery of anti-electron. Quantum field theory, of course, not covered in this lecture, and not covered in this course at all. And we haven't talked about this Stern-Gerlacher experiments yet. I have deliberately leave this one to the end of the course. Okay, so that's about the spins or the internal degrees of freedom that has no classical counterpart. Okay, before we leave, let's do a small quiz. Come back to this Planck constant. So what is the dimension of Planck constant? A, energy time. B, momentum length. C, angular momentum angle. D, energy. E, none of above. There could be more than one choices. All right, let me show the results. Okay, and it's wonderful. None of you choose D and E. So A, B, C are all correct. Okay, and actually, from Planck's quantization, you know the energy equals to h times the frequency. So that means the Planck constant equals to energy divided by the frequency. So Planck constant must have the dimension of energy and the time. Okay. From Bohr's quantization, you know, P integration over coordinates. And so that means the Planck constant must has dimension of momentum. This is momentum times the dimension of coordinates. That's length. From Kaufman's discovery that the angular momentum equals to m times h. okay, divided by 2 pi. So you can see that this is angular momentum. So that means the Planck constant must have a dimension of angular momentum and times angle. Angle is dimensionless. So both A and all of this A, B, and C are correct. And this D and E, of course, are not correct. Okay, so that is and this one, of course, tells us a lot about quantum mechanics. So you can see that later on, we can see that energy and time, momentum and the length, angular momentum and angle, they form so-called conjugate pairs. Okay. So this was this conjugation between those kind of quantities we already know in classical mechanics, right? And you can see that these are more deeply related in quantum mechanics. Okay, so that's a beautiful relation, and also a very intriguing, property of the Planck constant. All right, so this is this kind of a journey about this history of this early quantum theory, right? So don't worry about those formula. So just take fun in the stories. Okay, so later on, next time we're going to have a little bit more calculations so that we know how to proceed, how to do the calculation using this new quantum theory or the quantum mechanics. All right, so we stop here today. So if you have questions, please just feel free to ask. Okay, so let me